Chapter 4, Section 7. Inverse, wow, that's too much to take in all at once. Inverse sine function. First of all, let's look at a sine. If I look at a sine graph, looks something like this. Comes back that way as well. If you remember the inverse is going to undo an operation. So like addition and subtraction are inverse. Sine and inverse sine. So that's one notation. You will also see it written this way, and you need to not be confused if you see it written arc sine. That also means inverse sine. So if I have an angle, and I want to find the sine of the angle, well, I know the sine of the angle is going to be the opposite side over the hypotenuse, or y over r. So if I find sine of an angle, I get out this number, y over r. If I want to take the inverse sine, then I would take the inverse sine of the y over r, and I get out the angle. So we are wanting to be able to have a function for inverse sine, and a function means I get one answer only when I put values in. I get out only one number for the answer. Well, right now, if I look at the sine function, that's the angle that I'm putting in. So I take sine of an angle, and I get values between -1 and +1. So I want to be able to put in numbers between -1 and +1 and get an angle out. But this angle keeps repeating itself over and over again. So we need to have a section of this graph that only gives us one angle answer between -1 and +1. And if I slice here and here, I cover all the possible values between -1 and +1, and I'm not repeating myself. So we have to restrict the domain of inverse sine, so we only get one angle answer out of it. Second thing about inverses, if I graph them, they are reflections across the line y equals x. If I drew the line y equals x, it would be like that. And so if I reflected it, I'd get a little curve down there and a little curve up there. It would look like this green thing. Now we're going to look at their picture because it's a little better. Here is the sine function on the left between -π/2 to +π/2, which covers all possible answers. Reflecting it, this should look like my green thing that I drew. I'm putting in numbers now between -1 and 1, and I get answers between -π/2 and +π/2. It stops at this location. The unique angle y in an interval between -π/2 and π/2, such that sine of y is x, sine of the angle equals my number. The unique angle, if I'm going to find the angle, I take the inverse sine or arc sine, denoted like this. We can write it either way. So it might look like that, and my domain has to be numbers between -1 and 1, and my answers are going to be between -π/2 and π/2. We're going to draw that on a coordinate system. And if I do -π/2, that is down into the fourth quadrant, up to +π/2, that's the first quadrant. So inverse sine is defined in the first and fourth quadrant. In order to find an inverse sine of a number, or arc sine of a number, I am looking for the angle whose sine is ... I'm looking for the angle whose sine is 1/2. So if I wanted to do this by hand, I would first say, where are my sine values positive between quadrant 1 and quadrant 4? Well, if I think of my ACTS that we learned earlier about where trig functions are all positive here, cosine is positive in the 4s, so that means sine is negative. So sine is positive in the first quadrant, sine is negative in the fourth quadrant. That tells me if I want to find the angle whose sine is positive 1/2, I draw a first quadrant angle. Sine is opposite over hypotenuse, and I recognize this special triangle, and you recognize that angle is what? The angle is, oh, I wrote this wrong, square root of 3. Oh, well. Square root of 3 blue is what I wanted. What angle is that as I'm correcting this to square root of 3?
30.
That is a 30-degree angle. A 30-degree angle, or in radians, which is really what we want. Pi over 6. 1/6 pi. Pi over 6. There's the angle for arcsine of 1/2. Or what angle has a sine of positive 1/2? Pi over 6 does. We're repeating this. Same picture. If I have positive values I'm taking arcsine of, I'm going to draw a first quadrant. If I have negative values I'm taking arcsine of, I'm going to draw a fourth quadrant picture. So this one really just did it. Arcsine, they just wrote it as inverse sine this time, means the same thing. If a positive 1/2, I know it's a first quadrant angle, sine is opposite over hypotenuse. I recognize that that side matches for a 30, 60, 90, or pi over 6. So let's try this one. Inverse sine, negative root 3 over 2. So I'm trying to find the inverse sine of a negative angle. So I need to do a diagram down here. Sine is still opposite over hypotenuse. So I'm going to go opposite. I'm going to go hypotenuse. 1, 2, 3. Now this is negative. Which number does the negative go with in the picture? The negative square root of 3. Very good. So what is that angle right there?
60, 30. Oh, yeah. 60.
It's a 60 degree, or in radians.
Pi over 3.
A pi over 3. In fact, it's a negative pi over 3 angle. Because if I was wanting to know between negative pi over 2 and positive pi over 2, these are negative angles down here. So it's a negative pi over 3. That's the answer to inverse sine of that one. So let's try another one. Inverse sine of pi over 2. Now don't be confused by them throwing a pi in here. This is not an angle. This is still a number, just like negative square root of 3 divided by 2 is a number if you did it. In fact, what do you get if you take pi and divide by 2? Why don't you try your calculators? What number is that? Pi divided by 2. Okay? Do you remember what I said the domain of inverse sine was? Between negative 1 and 1. Because when we did the original sine, we only get answers out between negative 1 and 1. So when I do inverse sine, I can only put in numbers between negative 1 and 1. Is 1.57 between negative 1 and 1? No. No. Not possible. You cannot take, no solution. You cannot take the inverse sine of 1.57. You can't get an answer. You can't do it. All right, so now they are going to throw in things like the inverse sine of the sine of something. Now let's think through this English-wise a minute. Inverse sine means the angle whose sine is...
Positive. Oh, sorry.
Well, the angle whose sine is whatever this number is. Well, now they said the angle whose sine is the sine of pi over 9. Boy, that gets really convoluted, doesn't it? Let's just start with this part and see if we can make sense of it. The sine of pi over 9. If I drew a picture, we're not really doing inverse sine now, we're just doing sine of pi over 9. The pi over 9 angle would be a real small angle right in there, 1/9 pi. So I'd have some y value over some r value. It would be positive. So the sine of this happens to be y over r. And that's when I use this number, pi over 9, for my angle. Tell me the angle whose sine is this y over r. Inverse sine of this means what angle has a sine of y over r? Oh, the angle that has a sine of this y over that r is pi over 9. What color is a white house? Can I ask you that question? White. What is the inverse sine of the sine of pi over 9?
Pi over 9.
Pi over 9.
Because there's negative sine. So could you say that the inverse
Because they're asking me, give me the angle of the sine whose angle is pi over 9.
Can you think of it like in Uno when you do two reverses, it just equals the same?
Yes, that's what we're doing. Perfect. There's a good example.
It's like asking
Two reverses, you're just back to where you started.
So
Yeah.
you take the negative sign of the
The
sine,
inverse sine of a
it
sine,
just reverses it.
you're just reverse back to where you started with the angle. Now this is true as long as the angle they are talking about is in the defined region between negative pi over 2 and positive pi over 2, the first and fourth quadrant. And this one was, pi over 9 is in the right region. This one, where's 5 pi over 6? What quadrant is that if I drew 5 pi over 6?
1, 2, 3, 4. Third.
Second.
Is that okay? So it was.
Remember pi here, so if I'm 5, 6 pi, 5 pi over 6, I've got pi over 6 as my related angle over here. That's not in the defined region. Now, is sine positive or negative over here in quadrant 2?
Positive.
It's positive, ACTS. So when they give me an angle, when I'm doing this double reverse thing of the inverse sine of the sine, when they give me an angle that's outside of the defined region's over here, I need to write the angle in the defined region that gives me the same answer. Well, since it is positive here, where is it positive in our defined region?
Right.
Right here, in quadrant 1. If I have a pi over 6 angle in quadrant 1, I'm going to get the same answer as a 5 pi over 6 angle over there in quadrant 2. They'll give me the same positive answer. So now, if I'm taking the inverse sine of the sine of 5 pi over 6,
5 pi over 6.
the answer is pi over 6. I need to have the same angle in the defined quadrant. See, I can't use 5 pi over 6. I can't, because inverse sine is not defined over there in that second quadrant.
Okay, so if you had 3 pi over 6, is that in the same one?
So if, well, 3 pi over 6 is 1/2 pi.
So it would be 90.
So that would be 90 right over here.
What would your inverse be of that? Is 90?
So, well, what is the sine of 90?
The sine of 90 is...
It's 1. So what angle gives me a sine of 1? 90. That one works. Let's go to a calculator. We'll see more of those when we move on to cosine, stuff like that. Use a calculator in radian mode, because we're talking about radians, to evaluate these inverse sine functions. This is simply stick it in your calculator. Inverse sine of negative 0.81. But then I'm going to relate it back to by hand to make sure it makes sense.
Negative 0.944.
Is Christian right?
Yeah.
Okay. If I drew a picture that fits this, negative 0.81, now that's 0.81 radians. This would be negative 1.57 radians, because pi over 2 is 1.57. Positive 1.57. So here's my defined region in here. So if I have gone negative 0.81, I've got an angle something like this. There's my angle theta right there. So I'm going to have some negative y value over this positive r value. So it makes sense that, yeah, it could be negative 0.94. I don't know from drawing a picture because it's not a special angle. Now let's see if we can do this one. First on your calculator, then we're going to do it by hand to see if we can make it make sense. Take the inverse sine of the sine of 3.49 pi, and the answer is not going to be 3.49 pi because it's not in the defined quadrant, but your calculator knows that.
So negative 1.5.
Yes?
Yep.
Okay. So let's try this out. I need to figure out where this angle is. That's just short of 3.5 pi. Now a full circle is how many pi? 2 pi. So then I come around a full circle, and then I'm over at 3 pi, because I'm going all the way around. 2 pi, 3 pi, so just short of 3.5 pi, I'm just barely in the third quadrant down there. That's not in a defined quadrant. All positive inverse sine values are in this quadrant, and all negative inverse sine values are in this quadrant. So back over here, is sine positive or negative in that quadrant?
Negative.
It is negative in this quadrant. So that means I really need to draw the related angle over here in this quadrant. So this is my related angle right there. So I need to draw it in this quadrant. Right there, the related angle. So what I really have, this is, let's see, can you tell me, I need too many arrows, can you tell me the size of that related angle if it's 3.49 pi? How big is that? Remember, it's 3 pi when I get here. It's 0.49 pi.
Yeah.
There's 3 pi.
Oh,
3.49 pi. It takes me down there. It's 0.49 pi. So that means the correct angle is a negative 0.49 pi. On your calculators, take negative 0.49 times pi.
If you have negative 0.49 pi, doesn't that take you all the way back to the third quadrant again?
No. We start here. Negative angles go this direction. Just short of half a pi. Just short of half a pi.
But it's not 0.24 because 50 is halfway, isn't it?
Because like you would go all the way.
Now this is essentially just short of half a pi, right? 0.49 is not quite 0.5.
Mm-hmm.
If I went half a pi, I would end up straight down. That's pi over 2. Half a pi is straight down. Starting here, if I went half a pi, I'm just short of it, 0.49. And the same thing just short as this one was just short on that side. What's the answer to negative 0.49 times pi?
Negative 1.539.
Negative 1.54. Just like your calculator gave me right out there. We did it by hand down here. The answer should normally just be, oh, it's 3.49 pi, but it's in the wrong quadrant. So I figure out where 3.49 pi is. It's negative, so that means I need to draw the same related angle in the negative spot, which is the fourth. So a negative 0.49 pi is the correct related angle that takes me to the fourth quadrant. And so this is the answer exactly, approximately negative 1.54. Inverse cosine. If you think of the cosine graph, it starts here, and then it moves on like that, and then it would start repeating answers between negative 1 and 1. So in order to cover all the possibilities without repeating answers, we go between 0 and pi for cosine. So we're going to find that the inverse cosine is defined between 0 and pi. And here's what it looks like if you graph the inverse cosine. It would look like this thing here. So we can put in numbers between negative 1 and 1, and our answers will be between 0 and pi when we get our answers. We're going to treat it the same way as we did sine. All the definitions are the same, but we're defining it only between 0 and pi now. So inverse cosine or arc cosine, the domain is still -1 to 1. The range between 0 and pi, so 0 over to pi means I am using quadrant 1 for my positive and quadrant 2 for my negative. So instead of 1 and 4, it's going to be 1 and 2 for the inverse cosine. So if they ask me, give me the angle whose cosine is negative square root of 3 over 2. Well, since it's a negative value, I'm going to draw it in which quadrant?
You're going to draw it in 2. Sorry.
I'm going to draw it in 2. It's negative over here. It's positive over here. So I'm going to draw it over here. And cosine is adjacent over hypotenuse. So there's my adjacent. There's my hypotenuse. I bet that's a 1. I recognize it. What is the angle in here?
Yeah, 30.
It's 30 in there, so how many radians?
30 on the
5 or 6. So what is the true angle starting from the beginning? If that's 5 or 6 related inside. 5 pi over 6. 5 pi over 6.
So there's 4 pi over 6 in one quadrant?
There's 6 over 6. Oh, and what do you say that again?
Yeah, that one quadrant.
In the first quadrant,
Right there.
that goes from 0 to pi over 2, half a pi.
So,
And that's half a pi to pi. So that would be 0 to 3 over 6. And then from 3 over 6 to 6 over 6 is in quadrant 2. Inverse tangent. Now here's a whole tangent graph before it starts repeating. Keeps on going up. This one doesn't stop between -1 and 1. It just keeps on going up. So when we do the inverse tangent, numbers that we can put into it go all the way from -infinity to positive infinity. I can take the inverse tangent of anything. But my answers will be between -pi over 2 and pi over 2. -pi over 2 and pi over 2 are just like the sine. Positive values here, negative values here when you're talking about inverse tangent. All the same notation, inverse tangent, arctangent, they mean the same thing. The domain of this, though, is all real numbers. Anything can go in. And my answers are in quadrant 1 down to 4. So let's answer some of these. Find the exact value without using a calculator for these expressions. Inverse cosine of negative pi square root of 2 over 2. First tell me, since it's negative and it's inverse cosine, which quadrant I need to draw my reference angle in?
1, 2. Oh, sorry.
2. For inverse cosine, the positives are here. All of them have positives here. And the negatives over here.
That's a negative.
It is a negative. No, that's just a fraction. It's a negative value. So I'm going to need to draw my related angle right over here. This is going to be my related angle. My answer will be the true angle from standard position. This is going to give me the related angle. But square root of 2 over 2 is not a special triangle. Square root of 2 over 2, I'll stick the negative with it. Because they have already rationalized it is what has happened, so it looks different. So if you rationalize again, kind of, let's see what I get. What's square root of 2 times square root of 2? 2. Negative 2 over 2 root 2, which would equal negative 1 over square root of 2. There we go. I've got it back to the original before we rationalized it and got that square root of 2 over 2. So now I can say inverse cosine of negative 1 over root 2. So cosine adjacent over hypotenuse. Adjacent, hypotenuse is square root of 2, so I know that's the negative 1. Can you tell me the special triangle side over here?
-1.
Oh, sorry. It's, 45.
It's a 45, or a pi over
5. 4.
4. A pi over 4. So what is the angle standard position that goes all the way from 0 to get there? It's a quarter pi. So how much?
2. Oh, that's 2.
3/4 pi. 3 pi over 4 in order to get to this position. There's my answer. The inverse cosine of negative square root of 2 over 2 is 3 pi over 4. Let's try another one. This one is tangent. No problem. Approach it the same way. I'm going to draw a little diagram. Inverse tangent of this positive value. So which quadrant do I draw the positive ones in?
Go for the left side. Let's go to the left side.
Positive is always the first quadrant.
Yeah.
Let me do a little summary. Right over here. All of them are positive here. The ones that are negative down here, I use sine and tangent. Inverse sine, inverse tangent. Go down there. And the negative back here is where I'm doing an inverse cosine. So the negatives is the only thing that changes. Cosine, the negative ones are drawn in that quadrant. Sine and tangent, negative ones are drawn in this quadrant. So if I have a positive one, I'm going to draw it in this quadrant. Some sort of angle there that I'm trying to figure out. Well, that's square root of 3 over 1. Tangent is opposite over adjacent. Oh, 1, 2 square root of 3. What's that angle?
Oh, sorry. That's going to be 60.
60. Pi over 3. Pi over 3. It's the angle whose tangent is square root of 3. Pi over 3. Now they're going to pull our double negatives, our double reverses. The inverse cosine of the cosine of negative 1.1. Well, the answer is just this, as long as that is in the right quadrant. Now that's negative 1.1 radians. Remember, this is negative 1.57 radians, because pi over 2 is 1.57. So negative 1.1 is right there. There's negative 1.1. Is that the correct quadrant to draw my negative cosine, my negative inverse cosine values? No. It's the right quadrant if it was an inverse sine or tangent. Where do I draw my negative inverse cosine values? In quadrant 2. So I need to take that same related angle, draw a quadrant 2, 1.1 radians, right there. 1.1 radians. Same related angle, but draw it in quadrant 2.
That's not 1, negative 1, 1. Is that a 1?
That's 1.1. 1.1. So same size angle, but draw it in quadrant 2. Same related angle, 1.1. So my answer is going to be, what is the true angle that starts here and ends there? Well, this is 3.14 radians, right, pi. So how big is this green thing if that's 1.1 in there?
2.04.
2.04. That's the size of the angle. All right, so we're done playing around with that. Analyze. Oh, I guess it's not totally analyzing. Describe the end behavior of the inverse tangent function. Right here is the inverse tangent function. This one is the original tangent function. What's the end behavior is the inverse tangent function? As x approaches infinity, what is it going to? It's approaching pi over 2, isn't it? What's happening as my x is approaching negative infinity? Yeah, it's approaching negative pi over 2. So what's my end behavior? F of x, or inverse tangent, as x approaches negative infinity, this will equal negative pi over 2. As my function approaches positive infinity, it equals pi over 2. Okay, we're familiar with that, so that's old stuff, just applying it to an inverse tangent function. Okay, right here, I want to start with this part first. These equations are only true for x values in the restricted domains of sine, cosine, tangent. The inverse sine of the sine of x will simply be x, as long as it is in the restricted domain. If it's not in the restricted domain, then we have to redraw it and figure out the related angle. But these equations are always true. If I take the sine of the angle whose sine is x, What's the sine of the angle that gives me a sine value of x?
X.
X. These are always true. The cosine of the inverse cosine of x is x. So it could be the tangent of the inverse tangent of 7 is 7. Those things always work out that way. So that's
But
just...
you had 3.
Of 3? I could take the inverse tangent of 3. Tangent of the inverse tangent of 3 is 3.
I mean, like tangent of the inverse tangent of the tangent of 3. What would that be?
Oh, my word. The tangent of the inverse tangent of the tangent of 3? So the inverse tangent of the tangent of 3 is 3, and then I take the tangent of 3. I don't know what the tangent of 3 is. You'd have to do that on your calculator. It'd just be the tangent of 3. What if you took the inverse tangent of the tangent of the inverse tangent of the... Yeah. Let's stop. Let's just stop with 2. Composing trig functions with arc sine or inverse sine. So here they say, compose each of the 6 trig functions. We'll figure out what that means here. If inverse sine of x, angle whose sine is x. Inverse sine of x means the angle whose sine is x. So there must be some angle that when I take the sine of it, I get x. So that would have to be a triangle whose opposite was x and hypotenuse was 1. So that when I took the sine of it, I get x over 1, which is x. Now, I could find the missing side of this mystical right triangle. I know 2 sides. How can I find the third side in a right triangle? Just think way back. If I have a right triangle and I know 2 of the sides, what do I use to find the missing side?
Tangent. Negative tangent.
Way back to
Oh,
algebra
a squared,
1.
b squared, c squared.
Pythagorean theorem. Pythagorean theorem. So I can know that this third side, question mark here, I know that x squared plus question mark squared must equal 1 squared. So if I want to get to my question mark, I'll have to take the square root of...
X squared plus 1.
No, I have to subtract the x squared, right? 1 squared is 1 minus the x squared. There is my missing side. It is the square root of 1 minus x squared. So when they say compose each of the 6 basic trig functions using this scenario, well, that scenario gives me this triangle. So if I want to know what is the value of sine of that angle, well, you just look at the triangle and tell me sine is opposite over hypotenuse. What's the value of sine of that angle? It's easy answer. Don't make it hard.
Sine X.
The sine of this angle is opposite over hypotenuse. What is it?
1 over x. X over...
X over 1. X! I even knew that because the inverse sine of x means the angle whose sine is x. So what angle has a sine? The sine of that angle is x. Wow, I'm mixing it up. Cosine of that angle. Do the ratio for me in that right triangle. What's the cosine of that angle?
Question mark.
Well, it's not question mark anymore. We know what it is.
Square root 1 over square root of 1 equals that number right there, right?
Adjacent over hypotenuse. 1. There it is. What is the tangent of this angle?
Opposite.
Opposite?
X.
X.
Over square root of 1. Square root of 1 minus x squared.
There you go. Not going to rationalize it. Just going to leave it right there. You could, but just leave it right there. So then I can go, I've done these 3. What's my next one?
You got secant or cosecant.
Okay, I'm going to do cosecant next. What would be the cosecant of this angle?
1 over x.
1 over x. What would be the secant of this
1
angle?
over the square root of 1 minus x squared.
1 over the square root of 1 minus x squared. And the last thing, our cotangent of that angle.
Come on, negatives with the front.
What is it?
X.
Square root of 1 minus x squared over x.
Now, what does this do for me? Well, let's just take a real simple example of, let's take the sine of some angle. Let's take the sine of, no, I want to make an easier angle than that. Let's take the sine of pi over 2. I'm going to think of the sine graph to help me out getting this. That distance is 2 pi. That distance is pi. So that distance is pi over 2. What's the sine of pi over 2?
1.
1. It is 1. So the sine of pi over 2 equals 1. I wonder what the cosine of pi over 2 is. Oh, I just take the square root of 1 minus, x is 1 here, 1 squared. 1 minus 1, that's 0. 0. The cosine of that angle is 0. I wonder what the tangent of pi over 2 is. Well, my x is 1 in this case. 1 divided by the square root of 1 minus 1 squared.
Which is 1. So 1 looks like
1 divided by 6, undefined. This one is undefined. You see what I'm doing? Once I know one of them, I can get all of them by these formulas. These formulas will give me the value for cosine, tangent, cosecant, secant, cotangent. All I need to know is what the sine of that value is. And you could start with any of these and develop a right triangle just like we did and get a formula from, you could start with cosine, say cosine is x. And you could then develop formulas for all the other 5. And so if you knew what cosine was, you would know what all the other 5 are.
Quick question.
Yes.
It says reduce the composite function to an algebraic function without any trig function. What is it?
So these are all algebraic expressions not involving sine, cosine, tangent. They have no trig function in them. It's just an algebra equation. That's what they mean by algebraic expression involving no trig functions. Okay, the bottom of a 20-foot replay screen at Dodger Stadium. Right there is the 20-foot replay screen at Dodger Stadium. They need to get a bigger one. Is 45 feet above the playing field. So the playing field's way down there, 45 feet above the field. There's that screen up there in the air. As you move away from the wall, the angle formed by the screen at your eye is going to change. So if I'm looking up there at that screen, as I get closer to it, that angle gets bigger. And our eyes see size actually by the angle of the image that's coming at us. So as I get closer to it, it looks bigger to me. And as I get farther away, it looks smaller to me. But if I get too close to it, think of looking up here. I'm looking up at that screen. If I get too close to it, that angle starts collapsing on me again. Somewhere there is a distance from that screen where that angle is big as possible. That's the max, that's the ideal viewing distance. So whatever you're looking at, it will look the biggest to you when you are at that distance away. So when you're sitting in the auditorium and they're playing this math movie up there on the screen, which row do you sit in? So that it really looks biggest to you. Yeah.
Can we do that one day? Like, after this?
Yeah, you could go in there and measure it. You can answer this question. You'll have to take the same measurements as we do right here, but you could answer that question. So you need to know the height of the screen. You need to know how high the screen is off the floor. Now, the only problem with the auditorium is that floor slants. So it would mess it up a little. There is a distance from the wall that the angle is greatest. The picture's going to look the biggest. They want to know what's that distance, how far away from the wall. All right. So the angle right here is my theta. Right there is the angle I'm trying to find. Well, there are really two right triangles in here. The one that goes all the way to the top, and they called that theta 1. And then the angle that just goes up to the bottom of the screen, they called that theta 2. So if I want to know theta, well, the angle I'm trying to find is angle 1 minus angle 2. And I can find angle 1 by using the inverse tangent function, opposite and adjacent. I know, well, let me write to the side first. I know the tangent of angle 1 is going to be opposite, which would be 65, over adjacent, x. There's my x distance. So remember, if I'm trying to find angle 1, I take the inverse tangent of 65 over x. That will give me the angle. So if I want to know angle 1, I am going to need to take the inverse tangent of 65 over x. Minus, if I want angle 2, I'll need to take the inverse tangent of what?
45 over x.
45 over x. That answer is my ideal viewing angle, or that angle, that answer is what theta is, and I want to know the ideal theta, the biggest theta. So we need to look at a graph of this to see what it looks like. Got your calculators? I've got mine. Radian mode should have been already. Make sure you're in radian mode. Oh, I need to move it over so our recording gets it. Covered up part of it. Inverse tangent. So y equals. Turn off any plots if you have them, and clear off any equations if you have them. And again, make sure you're in radian mode, and that's what I need to do. Make sure I'm in radian mode. I am. We're probably going to want to manipulate our window before we try to graph it a little bit. So our x is our distance from the screen. So our x's would range from 0, we're right at the bottom of it, all the way to, I don't know how far away. 60 feet?
I don't know, 100, I can't even see it yet.
I'm going to try 100. My scale, oh, maybe I'll go by 20 since I go from 0 to 100. Now my y's, my answers to this are an angle in radian mode. So my minimum angle is 0. So minimum is 0. And my maximum angle would be 90 degrees. So that's pi over 2. Y max? Pi over 2, because I have them in radians here. So second pi divided by 2. Scale, I don't care what the scale is. Now I'm going to hit a graph. It's beginning to drop again, isn't it? So if I am 0 distance away, well, my angle would be 0. If I'm right here, I mean, it's flat. I can't see it. Angle 0. Somewhere in here is a maximum. So I just want to find it. So let's calculate, calculate a maximum. And, well, I'm not sure. But that looks like a good left bound. But I'm going to have to go a ways. Third way. And my guess is somewhere in between. Did it catch up with me? It did.
Yeah, that's right.
Where's the maximum? The maximum angle occurs when you are 54 feet away from that screen. So that's where you should sit. The picture will look the biggest. When will we ever use math? Well, now you know. That's right. That's the maximum spot. You get out.
Hi, Shishui.